So, today we will resume the algorithm, the PTRAS. So we will just work on the randomized PTRAS for the max-cut problem on dense graphs. Okay. So just to remind you what was going on. So the problem max-cut consists in find a cut S bar with S a subset of V that maximizes the number of edges between S and S bar. Okay, the number of edges in the cusp, and we call it the value of S bar. Okay, so we want to maximize this value. So So we know that this is MPRI. Okay. We know that we have a two approximation. Okay, which is a random cut. A random cut placed each edge of the graph in priority 1/2 in the cut. Okay, so it gives you a random cut. The value of a random cut is at least the number of edges over 2, which is clearly at least opt over 2. So we have a two approximation for a randomized two approximation for the problem. And by the way, this proves that opt is larger than m over 2. Okay, where m is the number of edges, because we know that if the expected value of a random cut is larger than m over 2, then there exists some cut which is larger than m over 2. So in particular, the optimum cut is larger than that. Okay, so what we are looking for here is a PTRAS. PTRAS is a polynomial time randomized approximation scheme. So a PTRAS is a family. It's an algorithm A of a graph G and some epsilon that outputs in polynomial time in n with arbitrary dependencies on epsilon. Okay, so for instance, so an example is n to the 2 to the 2 1 over epsilon time. This is polynomial in n. Okay, for me, and so this can be huge, but we don't care. Okay, the fact that we want is that for any fixed epsilon, okay, this is polynomial in n. Okay, this will not be that bad, huh? But this is the kind of thing that you can think of. So by the way, even there are some problems for which this is not even possible. Okay, this kind of dependencies. So that outputs in polynomial time in n. So we don't care about the dependency of. So n. What I mean by n is, I mean in fact polynomial time in the size of a representation of G. Okay, but since the size of a representation of G is a polynomial in n, then we can say it's polynomial in n. Okay, since the number of edges is bounded by n squared, that's fine. Outputs polynomial time, a cut S bar. such that the value of S bar is at least 1 minus epsilon times out. Okay, so we want to approximate up to epsilon the value, the optimum value. So, in order to do so, we will just look at a simpler version of this problem, which is the case of dense graph. So we say that the graph G is dense if the number of edges is at least alpha times n square for some fixed constant alpha. Okay, so we consider that alpha is fixed. Okay, and you can compute it in the algorithm if you like. Okay, you just need to count the edges and divide it by n squared, and you get the value of alpha. Okay, so you're given such a dense graph, okay, and you're asking the question, you're looking for an algorithm that will approximate up to epsilon the value of the cut. Good. So by the way, in general graphs, it is unlikely that such an algorithm exists, okay? Because according to some as likely as unlikely conjecture, which is the unique game conjecture, there is no, we know that unless p equals np, you cannot approximate max cut up to some constant, less than 1. Okay, so you need somehow to have simpler instances, and simpler instances are a graph with a lot of edges, or you can also imagine graphs, planar graphs. Planar graphs are also graphs for which you have this kind of algorithm, and all kind of other graphs. But in the general case, you cannot approximate better than some constant, okay, some given constant. So. And for this problem, we have somehow the best. We have somehow a proof that there exists an algorithm which is the best among all the approximation one. That is to say that we have an algorithm that gives you some constant factor approximation, and the proof that this constant factor approximation is the best you can do, unless some conjecture which is not really believed to be true, but anyway, is wrong. Okay. Why do I say that it's not that bad? It's because usually, until now, most of the results that were proved based on this conjecture turned out to be true also based on the conjecture P different from MP, but it was much harder to prove. Okay. So it's likely that this algorithm is optimal. Okay. Anyway, so in this talk we will focus on dense graph. So what do we know about dense graph? So we have a basic facts on dense graph. So we know that if G is dense, let's say alpha dense, but we will forget about it. So it's dense. If G is dense, then we know that opt is larger than alpha n squared over 2, okay? Because opt is larger than the number of edges over 2, so it's larger than alpha n squared over 2. And if you take and if LR is an optimum cut, what we can say is that the number of edges between L and R is larger than opt and is larger than alpha n squared over 2. Okay? But on the other hand, we know that this number of edges is at most the number of nodes in L times n, because the degree of every node is less than n. Okay? So this implies that the size of L and also the size of R is larger than alpha n over 2. Okay? So basically, the optimum cut will somehow be a constant fraction of vertices. Okay? So any part, both sides will be a constant fraction of the vertices. Good. Okay, so last time we've designed an algorithm to do so. So the first thing we've seen, so we designed an algorithm, and the algorithm was the following. So you pick, you will first sample the graph, and because of this thing here, that the optimum cut represents some constant fraction of the graph, basically the sampling will be efficient. Okay? With, it's completely unlikely that you will not sample correctly L and correctly R. Okay? It's completely unlikely that your sample is not representative of a graph. That's basically the key in this algorithm. Why do we hope that it will work? So basically what you do is you consider your graph G here. So this is G. Okay, and you do a sample. So you sample T random vertex. Okay. So you sample with replacement. You're allowed to sample a node twice. Okay. So S is not a set but a multiset. Okay. You're allowed to have some vertex which is represented twice with some multiplicity, but it's unlikely that you allow that. That's no big deal. Okay, and it will make the analysis much easier. So you sample some random vertex. Of course, they are anywhere in the graph, but I rearrange the drawing so that this set S is like that. Okay. So now what you do is T will be a constant. More precisely, it will be 1 over epsilon squared. Okay. So now what you do is that you have sampled a constant number of nodes. Okay? So because it's a constant number of nodes, you can enumerate all the cuts. Okay? It will cost you a constant time. Okay? So you can enumerate in time 2 to the 1 over epsilon square, 2 to the t, which is 2 to the 1 epsilon square, which is a constant, a large constant but still a constant. Okay? You can enumerate all the cuts. Okay? So this is called the technique which is called exhaustive guessing. So you will be able to guess the intersection of L, S with L. So you have here an optimum cut. Okay? LR that you don't know. You don't know it, it's the optimum cut. If you would know it, then P would be equal to 1P. Okay? So basically you don't know it, but the fact that S has constant size, okay, you can try all the possible cut of S, and one of them, you don't know which one, okay? But for one of them, you will have the right value. You will have S intersected with L correctly. You will have guessed it correctly. Okay, this is known exhaustive guessing. You don't know what you're doing, okay? But you know that at some point you will be right. And we will just focus on this case. We don't care about the other ones. Okay? Why we don't care about the other ones? Because we will try all of them and output the best answer among all of them. Okay? So, in fact, this is not what you do here. I wrote guess by exhaustive search L intersected with S. So what do I mean by that? Is that you try all possibility for L intersected with S, and then instead of outputting one cut here, you output the best among all the ones that you've tried. Okay? So what we will show is that when we have the right guess, the value of the cut will be of at least 1 minus epsilon times opt. And because we output the best among all of them, the output will be at least as good as that, as when the guess is right, so it will be at least 1 minus epsilon times opt. Okay? So because of that, we can just focus on the case where we've guessed correctly the intersection of the optimum cut with the sample. clear with everyone? Okay, so we guess that. So now, remember that L and R are both a constant fraction of vertices. Okay? So basically, since S is large enough with respect to epsilon, okay, this intersection here is representative of L and R somehow. Okay? And now what we will do is that for every vertex V, here, okay, for every vertex V, we will try to guess what is its degree with R and what is its degree with L. Okay, we will try to guess its degree based on the sampling. Okay, so how do we do that? What we've seen last time is that if we try to do it directly with, on the sample, it doesn't work. I gave you a counter example last time. Okay, that means that I gave you, if you try to say, okay, I can estimate the degree with L, by looking at how many edges are on the L intersected with S side, and how many edges are on the R intersected with S side. Okay? Then I can rescale this value, and the expectation, it will be the right value. Okay? If I rescale this random number here, which is random according to S, if I rescale the number by a factor, so we have a set here of size t, okay, and I have n vertex, so if I rescale it by a factor n over t, got it wrong here. It's n over t. If I rescale it by a factor n over t, then I have an estimator which is correct of the degree of V with L and the degree of V with R. Okay? Unfortunately, there are some fluctuation, and because we have many vertex here, this fluctuation can kill you. Okay? That's what we've seen before. So what you need to do is to take into account the choice you've made before placing V. Okay? You cannot place V to the left or to the right based on only this sampling. Okay? That's what we've shown last time in the first part. Okay? So how do you proceed? So we still use this as an estimator of the degree of V with L. Okay? But we will take into account too the degree of V with what we've done before. So how does this work? This works as follows. So we start with a sample here, S, okay? And we cut the graph into it. So we have the optimum cut. So what we will do is that we will try to take into account the fact that when we start placing people either to the left or to the right, we have to take into account of what we've done before. In order to take it into account, what we will do is that we will split the graph. We will do a random partition of the graph, okay, which is the partition V1, V2, V3 up to VL, and L will be 1 over epsilon. Okay. So how do you do this partition? The easiest way possible. So what you do is simply for all vertex V in the graph, you will place it in one of the VI with probability 1 over L, uniformly at random, independently for each other. Okay? So more or less, each of the VI will have size, an expectation n over L. Okay, but they may be a little bit larger or a little bit smaller. Okay, but more or less, each of them will have size n over L. Okay, and what you will do is you will place these guys one after the other, either to the left or to the right. Okay, so for the first one, you will only base your choice of on their degree with a sample. Okay? So what you do is that for the first one, you will just look at how many edges we have with each side, okay? L and R. Okay, so this is R with S, L with S. Okay? And if they have more edges to the L side, you will put them to the left, and more edges to the R side, you will put them to the right. Okay? So you will get a first cut which is A1, B1. Okay? Later on in the algorithm, we will forget about the sample. We will have construct the cut up to let's say vi minus 1. Okay, so we have a cut ai minus 1, bi minus 1, and this is vi minus 1, and now we are about to place the guys in vi. So how will we decide how to place them? We will do the following. For each of these guys v, okay, we will use their exact degree with the current cut we've constructed up to now. Okay, so we will look at its degree with the current cut we've built. Okay, so we look at the exact set of edges that is going to the cut that we've constructed up to now. We will completely ignore the edges in VI. Okay, why? Because VI, the size of VI, remember it's about n over L, which is epsilon n. Okay, because L is 1 over epsilon. Okay, so the number of edges inside VI is at most epsilon square n square. Okay, it's at most epsilon square n square, which is less than epsilon square times opt.
Is this a principal thing that we forget this?
Speak louder, please.
Is this, I mean, is it important that we ignore this part, or it's just...
No, that's what I'm showing here. It's that we don't care.
So
we don't care, because basically, the number of edges that we will lose, that we will not take into account, will be about of n square, epsilon square times opt. Okay? And there are L such set that we will ignore. So when we multiply it by L, which is 1 over epsilon, it will be epsilon times opt. Okay? So we don't care about epsilon times opt.
So if you don't care, would it be easier to include it?
No.
Later
No. It will make the analysis more complicated. So for the algorithm, it will definitely be better, but the analysis will get much more terrible. Okay. So yeah. So that's an issue. Okay. In algorithm, you have a choice of either having a simple algorithm. Okay, but it might be harder to analyze, or you have to find a trade-off between the complexity of the proof and the complexity of the algorithm. Okay, so in the teaching case, you better have a not too complicated algorithm and simpler analysis than the converse. Okay, so it depends on how much time do you have. But for the best algorithm is the simplest algorithm is you sample, and then you just do. This step without gathering the nodes in VI. Okay, that means, okay, I'll talk about that later on. But you have a very simple algorithm, but the analysis is terrible. I mean, it's very complicated. Okay, but you show that the simple idea that you have is easy to indeed works. Okay, but the analysis is terrible, and I don't want to get into that, and I would not be able to do it anyway. So, okay. So what do I mean by that? So you forget about the edges here. Okay, you just forget about them. That's basically what I do here. Okay? So you count the number of edges that V has with the current left part of the cut. Okay? And now you don't know what this is. Okay? But you know that you have a faithful estimate of it. Okay? So you use EV, which is the estimation of the degree of V with L, that you rescale correctly. Okay? And how do you rescale it? So basically you have here the vertex set from Vi plus 1 to Vl. Okay? So you need to rescale it by a factor 1 minus I over L EV. Okay? So you estimate that the degree here is 1 over I minus L times EV. Okay? This will be correct on expectation. Okay? So basically, what is this FV here? This FV is in two parts. First is the degree of V with the already constructed left part of the cut. Okay, so FV is basically the green edges here. Okay, this is FV plus the estimate of the number of edges that V has with L intersected with the following parts that have not yet been placed. Okay? So we don't know what this value is, but we know that this is a faithful estimator of the number of edges. Okay? So we say that for V here, this FV is hopefully, this is our estimate of the number of edges of V with the left side of the cut, which cut? A1 union AI minus 1 union L intersected with VI plus 1 VL. Okay, and this, let's say that this is SI. Well, I don't care. It's, let's say it's lambda I, and this is V minus lambda.
The original sample is A1, B1. The original sample, this is A1, B1?
No, the sample is S, and I forget about it. Okay, I just used it. I just used it once to compute this EV. Okay? I just used the sample once to compute EV, and then I forget about the sample. I won't use it anymore. Yep.
So you build the A1 and B1 just with the...
Based on EV. Okay? I have nothing else to base on. Okay? But it's not that bad, because maybe it's all wrong, okay? But it only concerns a fraction epsilon of the vertices. So there will not be too much damage. Okay? Hopefully.
Yeah, I think so last. I mean, because at the end you do this algorithm only on those which you didn't sample, no?
No, I do it on everyone, even the one I sampled. Yeah, I've already guessed this intersector with L, but I don't care. Okay? Okay, it might be inconsistent with each choice, but I don't care. Okay? Good. So now I have to decide whether V will be placed either to the left side or to the right side. So what I want to know is if V has more edges with the left side, then I will put it to the right. And if it has more edges with the right side, I will put it to the left. And how do I know if it has more or less edges? I just compare the number, our estimation of the number of edges it has to the left side with its degree where I remove vi over 2. Okay? So if fv is larger than the half of its degree, then this means that v has more edges with the left part, so I put it in the right part, I put v in bi. Okay? If fv is less than its degree over 2, then v has more edges with the right part, so I put it in the left part, I put it in ai. Okay?
There is some inconsistency in the right here, because still you write in step 3, you write for all v in v minus s.
In what?
In step 3.
Oh yes, okay, sorry. Okay, done.
Does it change anything at all? Because last time you did all the argument.
Yeah, but I did not do the proof last time. This time we will do the proof, so we need the correct algorithm. Okay. Basically, what I mean by that is that when you do the proof, you correct the algorithm at the same time. Okay. It doesn't change anything because S is it's a constant number of vertex. Okay, so you can always manage, but this simplifies the proof to proceed this way. Okay, thank you. And now you output bucket. Okay, when you're done. Okay, so everybody understand the algorithm? Yep.
Just I didn't get really the guessing by exhaustive search L cap S,
Okay.
the step 2.
I need to explain it correctly. Okay. So this is a very important argument. So so basically, what do I mean by guess is let's rewrite the algorithm differently. Okay? So I replace 2, step 2 becomes for all cut, let's say lambda row of S, okay, do for all cut, let's say yes, lambda row of S, do step 3, do step 3, 4, 5, step 3, 4, 5 with L intersected of S equal lambda and R intersected with S equals rows. Okay? Then let the A lambda B lambda equals to the output cut. That is to say A lambda equals A1 union L and B lambda equals B1 union BL. Okay? And now I say output the cut A lambda B lambda but maximize the value of A lambda B lambda over all cut lambda row.
Okay, you just take the best cut.
I
for
just output the best one. Okay? And what I claim is that there is only one iteration of this that we need to analyze. This is the case where the guess is correct. Okay? If we can show that when the guess is correct, the value is at least something, then the best among all of them will be at least something. Okay? And by the way, I would be completely unable to analyze the value that we get if the guess is incorrect. Okay? Because my estimator will not be correct. So I will explore an exponential size space, but the exponential of a constant size, an exponential in a constant size space, okay, but there is only one spot here that where I can tell something, okay, but since I explore everybody, okay, I can assume that I know which one I can assume that I am at the spot where the guess is correct. Okay? So basically, if you want to think about it, it's basically what you do is that in an NPR problem, okay, you have a huge set of size, basically more or less 2 to the n. Okay, the number of cuts in a graph of size n, with n vertices, is 2 to the n. Okay, and so if we want to solve to find the optimum, we have basically we can say that I will do an exhaustive guess, okay, but it will cost me to try all the 2 to the n cuts. Okay, and I will be able to find the optimum. What we do here is that we sample a small set of vertices, a constant size set, and then I can guess in this much smaller space the size, the exact cut, because it's constant size. Okay? So now, what is the complexity of this algorithm? It's simply, so for all this cut, I will do it 2 to the 1 over epsilon square 2 to the t times, okay, which is 2 to the 1 over epsilon square, okay. I have to enumerate all the cuts of a set of t vertices, where t is 1 over epsilon, okay. So it's 2 to the t, so the time complexity will be 2 to the 1 over epsilon square times the time complexity of step 3, 4, and 5. And these steps are basically, I think that we can manage to do it in linear time, but okay, let's say, to be rough, n squared. Okay? So we will be in the case of a randomized polynomial time algorithm. Okay, the time is polynomial. It's even what's called FPT. So you have a fixed parameter algorithm. Okay, you fix epsilon, and then you have a time which is independent of epsilon. Okay. Is it okay with you? Good. So I can now assume, everybody is agree with the fact that now I can assume that I've guessed correctly the cut, the intersection of the optimum cut, of unoptimal cut with the sample. Okay? It's just because I will go through every cut. So for one of them, I will be okay. It will be true. Okay? Good. So, okay, so now we need to analyze that. So I told you last time that we would do hybridation. So this is a very important technique. Okay, this is a technique that you will see many times, that is used many times in probabilistic algorithm. So basically, what do we want to compare? Is we want to compare the value of the output of our algorithm, which is this cut here that we have obtained. So where we have AI and BI here, A1, B1, AL, BL. Okay. So you want to compare this, the value of this cut, with the value of this cut, which is the optimal cut, but you don't know anything about it. Okay, the only thing that you know is its intersection with S. Okay, that's the only thing that you know at the beginning. Okay? So basically, if you want to do it directly, this will be complicated. Okay? But what you can do is try to do it by hybridation. You will try to do an hybridation between these two cuts. And what you do is that basically what you will do is that you will study how much you lose, how much value you lose when you shift to the right, and where basically what you do is that how much you lose at the highest step of the iteration. Okay? At the highest step of the iteration, you will decide for the vertex in VI. Okay? And what you will look is basically what's going on at the highest step. So basically what's going on is that in the optimum, the step before, you had this cut. At the step I minus 1, let's see. So this is step I minus 1 here. So basically what you have is that you have placed the guy either to the left or to the right, assuming that you have already this cut ups, you have already placed this guy in A1 up to AI minus 1 and AI minus 2. Okay, so you place this guy. And below, you still assume that you have the optimum cut that you estimate thanks to your estimator based on the sample. Okay? And you will compare this cut with the next one. Right, and here you have the optimum cut. LR. Okay? So basically at the end of step I, you will have placed this guy in AI and PI, and you will still assume that you have the optimum cut below. Okay? And basically what we will try to bound is how much we lose between step I minus 1 and step I. Okay? We try to bound this difference. So if we are able to bound this difference for each of this, then we are able to bound the difference of this first set with this last set, which is exactly what we are trying to show. Okay? So formally, what do I want to do? Formally, what will I do is that, so let, how to call it? Let's say, so this is called hybridation. Let's say hybrid. I don't know what hybridate. Let's say this word exists. Let's hybridate. Okay, we will hybridate the cuts. Okay. The optimal cut with the output of the algorithm as follows. So let HI be the IF hybridation between these two. Okay? So for I equals 0 to L, for I equals 0 to L, let's hi be the hybridation, which is A1 union AI. Okay, so this is the left side. Union L intersected with Vi plus 1 Vi plus 1 VL. Okay, so this is the left part. The left part consists in the first I set of the output of the algorithm, followed by the optimal cut for the next vertices. Okay, and the right part is simply the complementary set, and the complementary set is B1 union BI union R intersected with VI plus 1 union VL. Okay, so this is the cut that we will consider. And what we know is that, by definition, by construction, H0 is the optimum cut, LR, okay, and HL is AB, the output of the algorithm. Okay? And now what we want to bound the value of the optimum value minus the value of the output of the algorithm. Okay, so this is the output. And what we do is that we simply rewrite it as the sum for E going from 1 to L of the value of HI minus 1 minus the value of HI. Okay, so we want to bound from above this value. We want to show that these two values are close to each other. This is not much less than this one. And in order to do so, we just rewrite it as a telescopic sum, okay, as the sum of the difference between these two hybridations, the value of these two hybridations. Okay? So why is it nice? Why is it nice? It's because basically now I have just to compare that with that. That is to say, how much do I lose when I place these guys? When these guys move from the optimum cut to this AI and BI. And this is exactly what my algorithm do. Okay? It has already constructed that. Okay? And at the time it's placing these guys, this is exactly the information he has. Okay? It knows where he has placed the other ones. Okay? These are choices that are irreversible, that it will not change afterwards. Okay? And this optimum cut here is exactly the situation where he is. He will try to guess, okay, what the value of L and R are, and based on that, he will try to make the best choice. Okay, so we need just to now where does the algorithm lose something here? It loses basically with this estimation here. Okay. And this estimation, we know how to control it. Okay? So now we will just try to bound, okay, the difference between these two cuts. These are cuts which are fixed. Okay? You run the algorithm, and now you have the cut HI. Okay? And now what you will try is to bound the value of HI minus 1 with HI. Okay? There is somehow nothing random anymore. Okay? You run the algorithm, okay? And then you have this sequence of cut, and you want to bound the difference between two of them. Okay? and we will get the bound that we want by summing over all cuts. Good. So now let's take I between 1 and L, and let's bound this value. Okay? So I will erase here. So let's do the drawing. Let's draw the situation. The situation is the following. So let's write G here. So this is G. Okay. So we are looking at VI. Okay. And here we have A1 up to I minus 1. This might be empty. If I equals 1, it's empty. Okay? V1, Vi minus 1. And here below, I have L and let's do it in red. I have L and R. Okay? So this is the situation. And now I have the nodes here, but I have to decide either to place them to the left or to the right. Okay? So there will happen two things. So in HI minus 1, they are placed partitioned this way. Okay, they have the optimum partition here, intersected with. And in the cut HI, they will be partitioned like that. Okay? So now I have to compare what's the difference between these two cuts. Okay? So clearly, this difference between these two cuts, the only thing that matters are the edges that have at least one extremity in VI. Okay, for the others, it's the same. The two cuts have the same value. Okay, either for edges that have both of their extremity outside VI, this choice does not affect the value of the cut. Okay, so we just need to focus on the edges that have an extremity in VI. Okay, the difference in value will only be there. Okay? So let's look at these edges. So basically, if the algorithm found the right answer, no matter how, okay, we don't care. Okay, if, as in this drawing here, these guys are placed in both in Bi and R, and these guys here are placed both in R and I, this is good. Okay, it doesn't change. The problem is the guys that are placed, for instance, to the right, and that should be to the left. That are placed to the right in HI, but would be placed to the left in HI minus 1. And the question is, why would the algorithm do that? Okay? And the answer is because I thought it was the right answer. And what could go wrong? This cannot go wrong. Okay? This is the correct estimate of the degree of this vertex with the upper part. The only place where it can go wrong is the estimate with the optimum. Okay? And by how much can it go wrong? It can only go wrong by how far the estimate is from the real value. That's what we will show. So basically, if I am wrong, if I make the wrong decision, how many edges will I lose? I have a correct estimate of the number of edges with the upper part. Okay? So on this side, I cannot lose edges somehow. The only place where I will lose edges is because of my estimate with the lower part is wrong, and how much edges will I lose? At most, how bad? This is bounded from above by the distance between the estimate and the real value. Okay? More or less. That's the spirit of it. So let me finish and then I'll take your question. So basically, since basically my choice here is linear in the estimation, okay? If I place it on the other side, okay, I thought I would be putting more edges, but in fact I put less. But how much less did I put? No more than the difference between my estimate and the real value. Okay? So I can bound how much I use by the distance between the estimate and the real value. And this is something on which I have control because I know that this estimate is correct on expectation. And it's stacked. I mean, it's sufficiently concentrated around this value, so we'll be able to bound. Okay? So let's now prove it. Okay, so let's assume that the algorithm made the wrong choice. And we will try to bound how much edges I lose. Okay? So what do I want to say is basically the difference in value between these two, okay, the difference in value between these two cuts, okay, is the sum over V is no more than the sum over V in VI, such that V does not belong to the same side in HI and HI minus 1 of how much edges I lose on V. Okay, so this is just an informal, semi-formal formulation. Okay. Plus, basically, I will just ignore. Remember that in the algorithm we ignore the edges that are between Vi and Vi. Okay. The number on V with V outside of Vi. Okay? So I look at all the V in Vi. Okay? And where do I lose is when I do not make the same choice. Okay? When I move V to the left, when it should be to the right. Okay? So V does not belong to the same side in HI and HI minus 1. And what do I look is the number of edges that I lose on V with the outside of Vi. Okay, I just count the number of edges that V has with the outside of Vi. So let's look at V here. Okay, and I look at the number of edges that I lose if I move it to the right or to the left. Okay, just look at the outside. I do not look at the number of edges that V has with the inside of Vi. Okay? And why do I have less or equal? Is because the number of edges are inside. The number of edges inside, I just upper bounded by all the edges. Okay, I can just assume that I will lose everything. Okay, I made it completely wrong, and I end up with a cut where all the edges between two nodes in Vi were put on the same side. Okay, so this is So I assume this is worst case. This is the worst case that